So the next thing we want to cover is molecular, total ionic, and net ionic equations. There are three different ways we can write equations. So far, we've been writing molecular equations. A molecular equation is where every compound is written in its neutral form. This is the most common way. This is the way you guys were taught in Chapter 4, and honestly, this is the way you're going to write them the bulk of the time. But total ionic and net ionic equations are important because total ionic shows us everything that's in solution, whether they be spectators, meaning that they're not participating in any sort of the reaction, or the actual ions that are participating. But net ionic are really important because they actually they're showing us what we call the driving force of the reaction. They're showing us what's happening and why. So molecular equation, every compound is written in its neutral form. An example to this, let's do silver nitrate. Silver nitrate in solution and sodium chloride. So I have a beaker of sodium nitrate, or silver nitrate, I apologize. I have a beaker with silver nitrate in it, and then I have a second beaker full of NaCl. And I'm going to pour the two together and see what happens. It's going to form silver chloride and sodium nitrate. How do I know that? Well, one, we're going to cover double displacement reactions in a little bit. But two, I know that silver chloride is insoluble, so that's going to form. A total ionic equation asks, is it a strong electrolyte? Is each individual species a strong electrolyte? If it is a strong electrolyte, we write it as separate ions. So, I know silver nitrate is a strong electrolyte. Nitrates are always soluble. So I'm going to write that as Ag plus NO3 minus. Silver chloride, another strong electrolyte. Sodium ions, always soluble. Chloride's usually soluble. Na plus Cl minus. Silver chloride, not soluble, not a strong electrolyte. So I write that together, AgCl solid. And then sodium nitrate. Sodium nitrate, sodium always soluble, nitrate always soluble, so that is also a strong electrolyte. I have sodium ions and nitrate ions. This entire thing here is what we call your total ionic equation. It shows every single species in the reaction mixture, in your pot, in your beaker, in whatever you're doing your reaction. It shows every single thing there in whatever form it will be while it's floating around in solution. Remember, ions float around as ions in aqueous solution. Net ionic equations removes your spectator ions. A spectator ion is an ion that is present on both the reactant and product side of the reaction. If it's present on both sides, what it really means is that it's not involved in any of the chemistry. It's not doing anything. It's behaving as a spectator. It's sitting back while everything else happens. So in this case, what I do to find the net ionic equation. Net ionic removes all the spectators, write everything else. I look and I say, okay, I've got silver here, silver plus. I don't have any silver plus on the other side. So I'm going to go ahead and write down silver plus. I've got a nitrate here, I've got a nitrate here. I'm going to cross those out because it's on both sides of the reaction. I've got a sodium here and a sodium ion here, and you do have to make sure that they're balanced. The reaction was balanced to start, but one sodium, one sodium. I've got one chloride ion here and no chloride on the other side. That's all of my reactants. Now I look at my products and I have 1 mole of AgCl solid on my product side, and it's the only thing there. This is what we call your net ionic equation. Your net ionic equation is important because it shows you the driving force of the reaction. It shows what's really happening. It's helping us identify why the reaction goes forward, why anything happened at all. In this case, the driving force of the reaction is the formation of silver chloride. So again, net ionic equations are really important because they show us the driving force. They show us what's really happening. We're going to use net ionic equations some in this semester, and we're going to use them a lot in second semester. So you need to be able to be comfortable with them. And then don't forget them when we finish this unit, which a lot of students do, because they're going to come back and you're going to use them a lot in second semester. So let's go ahead and work some examples. So the first example has acetic acid and sodium hydroxide reacting to produce sodium acetate and water. This one's kind of tricky because acetic acid is a weak acid, which means it is not going to completely separate into its individual ions. Some of it separates, which allows it to react, but not all of it. So for the reaction, I'm going to continue to write it as a full acetic acid molecule. Now, it's asking for the net ionic equation here. Oftentimes, it's easier to go through your total ionic to get to your net ionic. So I'm going to write down the individual total ionic species above the reaction so we can write the net ionic equation below. So this I'm going to still write as acetate because, again, some of it, a little bit of it, does break apart. I do get some acetate ions and some protons in solution. But the majority of the molecules stay together as an acetic acid molecule. This gives me sodium and hydroxide ions. Sodium acetate gives me sodium ions and acetate ions. And water stays in the form of water. So when I look through here, the first thing I want to do is get rid of all my spectators. I see that my spectator is sodium plus. It's a common spectator. The driving force of my reaction is the formation of water. So the net ionic equation here will be acetic acid plus hydroxide, giving me acetate and water. (2Ki plus Br2) giving me 2KBr plus I2. So I've got potassium iodide reacting with molecular bromine, producing potassium bromide and molecular iodide or iodide solid. This does split up into K plus and I minus. This does split up into K plus and Br minus. So my spectator here is that K plus. I've got K plus on either side of my reaction. My net ionic would be 2 moles of I minus, because there is 2 of each of these here. There's 2 of each of these here. 2 moles of I minus reacting with 1 mole of Br2 liquid to produce 2 moles of Br minus and 1 mole of I2 solid. And the last example here, calcium carbonate solid plus HCl aqueous gives me calcium chloride aqueous, water, and CO2 gas. Calcium carbonate's not going to split up at all. That's going to stay together because it's a solid. HCl is a strong acid, so this will separate into H plus and Cl minus ions, and there's 2 of each. Calcium chloride is soluble. This is going to split up into calcium 2 plus and 2 moles of chloride ions. Water will not split up and carbonate will not split up. So just so that they look different and don't completely blend in color, I'm going to write this in pink. We've got calcium carbonate. Here, chloride is my spectator. Calcium carbonate is going to react with 2 moles of H plus, producing 1 mole of calcium 2 plus 1 mole of water and 1 mole of CO2 gas. So, the driving force in this first reaction, formation of water. The driving force in the second reaction, forming I2. Driving force in the third reaction, we're forming water and carbon dioxide gas. There are more examples of this in your homework, in your textbook, online homework, end of the chapter, etc. Please, please, please practice some of these because, again, we use them in this chapter and then we don't really harp upon them much, but we bring them back heavy in second semester without much review.